the last video cut out on me a little bit, so I just want to finish this problem. So remember, what we were doing here is, we took this amount of joules, 4.42 times 10 to the minus 19th. We converted it into electron volts, and of course we get 2.76 2.76 electron volts, which of course was the the answer that we got before using the constant 1,240 nanometers times electron volts, or electron volts times nanometers. It doesn't matter which one you put first. All right, so let's do problem B, which I've already set up, you can see. So with problem B, they want to know, what is the energy for a photon that has a wavelength of 200 nanometers. Just as a reminder, in part A, the wavelength was 450 nanometers, and so we get and by the way, that's in the visible part of the spectrum. So you get that photon would have an energy. So just one single photon would have an energy of 2.76 electron volts. What we're going to see here is, and this is something I really want you to understand and appreciate, is when we go from 450 nanometers to 200 nanometers, the energy is going to go up, right? Because the number in the denominator gets smaller, and therefore the energy will go up. All right, so we cancel the nanometers as I've already done, and the answer comes out to be 6.2. All right, 6.2. So when you do this, 1,240 divided by 200, you get 6.2, and the answer, of course, is in electron volts. All right, notice you get a bigger number with 200 nanometers than you do with 450 nanometers, right? So this is actually in the ultraviolet range, this 200 nanometers. The human eye can't see that. All right, so now we could even convert this to joules, or we could do it the other way, and in fact, let me set that up. All right, setting this up using the other version of H times C. These are just different units. Of course, is 1.989 times 10 to the minus 25th, and those units are joules times meters, which means, of course, the wavelength, lambda, which was given to us in nanometers, must be converted into meters. So you just replace the metric prefix nano with what it is, times 10 to the minus 9th. That's what nano means. So you're dividing this number by 200 times 10 to the minus 9th, and then of course the meters cancel, right? Which is what we want. The meters cancel, and you get this number, 9.945 times 10 to the minus 19th joules. But remember, the problem asks us to do this in nanometers, which I already did. But I just wanted to show you this will give us the same answer. So once you divide those two numbers, you get, let me look at my calculator here, 6.21, something like that. But anyhow, about 6. I think the last one we just said it was 6.2 electron volts, right? So, which is exactly what we got earlier by using the 1,240 electron volts times nanometers as the constant. All right, so it works either way. I just wanted to show you that. All right, so I've set up the second problem. So that it asks us, what's the energy of a photon? It's actually a radio wave that is in electron volts. They want to know the answer in electron volts. But this time they give us the frequency, and they say the frequency of this is 100 gigahertz. All right. So this is like in the it's actually more in the microwave region, but that doesn't really matter. The idea is we really have to just convert this from Well, actually, there's actually several ways to do this, right? We have to convert this from gigahertz to hertz. We could also change the units to, we could change to the wavelength as well, right? Because we have this equation that the energy is equal to the speed of light times h times the speed of light divided by the wavelength. Right, so we have that equation, but that's also so there's an alternate way of doing this. Remember, the original equation that Planck came up with was it's h, Planck's constant, times the frequency. So again, you could change the wavelength, and that's you could change the frequency to wavelength. That's perfectly fine. The one thing that you do have to do is the gigahertz has to be just in hertz, not giga. So it would be 100 times 10 to the ninth, right? Because that's what giga is, and it's hertz, which hertz and 1/seconds are the same thing. And so the answer comes out to be, let's see, what is the wavelength? 0.03. So 0.00. Oops. Sorry. Not. It's 0.003 meters. All right. So that would be the wavelength. Again, you could do this, and I'm going to set it up both ways, and we'll calculate it. Both ways. Okay, so we'll use the wavelength, and then we'll also just use the frequency more directly, like with this equation right here, Planck's constant times the frequency, as long as the frequency is in hertz. But our answer will be in joules, so we'll still have to convert to electron volts. All right, so you get a wavelength of 0.003 meters, and then if we use the Planck's constant times the speed of light in meters per second, you get this constant 1.989 times 10 to the minus 25th joules times meters, and the meters cancel. And the answer, so you just do this numerically, the energy of the photon, which is ultimately the answer that we were looking for. The energy of the photon is what does it come out to be? 6.63 times 10 to the minus 23rd. And it's of course joules. And so you can convert that directly, right? If you remember the conversion between joules and electron volts, 1 electron volt is 1.6 times 10 to the minus, that's a 10 to the minus 19th, and that's joules. And of course the joules cancel. And our answer comes out to be, in electron volts, what do we get? Oh, it's really small. It's very, very small, right? Because this is something like in the microwave to radio region. So it would be it turns out to be 4.14 times 10 to the minus 4th. 10 to the minus 4th electron volts. All right, and I promised you I was going to show you the other way to do this, and so let's do that directly, right? More directly, I guess. So the energy is equal to Planck's constant, so it's h times the frequency, and so remember Planck's constant is 6.63 times 10 to the minus 34th. And they give us a frequency of 100 gigahertz, but remember we have to have that, we have to change the metric prefix giga into what it is numerically, times 10 to the minus 9th. I'm sorry, times 10 to the, sorry, not, times 10 to the 9th, to the positive 9th. gigahertz is times 10 to the positive 9. I gotta make sure I didn't do that wrong in the last little segment. I don't. No, I think I did that right. Okay, so yeah, times 10 to the 9th. I don't know why. So it's to the positive 9th hertz. So sorry about that. And so that comes out to be, let's see. So that comes out to be, when you do this calculation, remember it's times 10 to the positive 9th hertz, right? That's what gigahertz is. It comes out to be 6.63 times 10 to the minus 23rd, joules. Sorry, that's a 2. All right, and notice that's exactly what we had up here. And then all we did is we converted it, and so if you do the same thing with this number as we did with this number, with our conversion, you just divide by 1.6 times 10 to the minus 19th. Either way, you're going to get this very small amount of electron volts, 4.14 times 10 to the minus 4th electron volts. They're setting up problem 3. They want us to know what the wavelength of the following energies. And they want the wavelength in meters. So let's indicate that the wavelength has to be in meters. And the first part A, if the energy of a photon is 2 electron volts, what's the wavelength? If the energy of an electron, not electron. If the energy of a photon is 2 electron volts, what's the wavelength of the photon? If the energy of the photon is, remember we're talking about light, 0.1 electron volts, what's the wavelength? And if the energy is 5,000 electron volts, what is the wavelength? Okay. All right, so remember, the greater this one, obviously C is the largest wavelength, so that's going to give us the smallest, the C is the largest energy, and so that gives you the smallest wavelength. All right, this one, of course, is B is the smallest smallest energy, and that'll give you the largest wavelength. All right, so let's get into it and do this problem. So starting with A, we start out with 2 electron volts. The conversion between electron volts and joules is in this fraction. So 1 electron volt is 1.6 times 10 to the minus 19th joules. You just multiply those two numbers and you'll get an answer in joules. And the answer that we get is, let's see, let me make sure I'm looking at the right one. 3.2, so 3.2 times 10 to the minus 19th joules. All right, so that's fine. I mean, that gives us the answer in joules. But remember, we have really this equation. Here, let me set it up over here. We know the energy is equal to a constant, h times c, divided by the wavelength. But look, if we rearrange this equation, if we know the energy, we can rearrange this equation and solve for the wavelength. So that rearrangement, algebraically, you just, the lambda and the e switch places, and so the wavelength is going to be equal to hc in the proper units, divided by the energy. All right, since the energy is in joules, we're going to use this. We're going to use this for the 1.989 times 10 to the minus 25th. Minus 25th. That's a 5. Joules times meters. Joules times meters. Right, and then we divide by the number of joules for that particular photon. So it's 3.2 times 10 to the minus 19th, and of course it's joules, and then the joules cancel, and then our answer will be in